Now that we have covered how a single neuron works, we are going to interconnect multiple neurons and see how we can build more complex neural networks out of those and how they can be used for training. So I gave the analogy that if you think of a single neuron as driving a car in which you have only a few controls, like you can change some of the weights, and you move on to multiple neurons, it's kind of like a jumbo jet or a space shuttle, something like that. It has a number of moving parts, and it's really important to understand what each of those parts do so that we can design an effective neural network that would generalize to novel problems. So we've discussed how a single neuron works, and it's pretty simple. What a neuron does is simply takes in, this is a single neuron, it takes in all of its inputs. So let's say we've got an input x1, we've got an input x2, and up to so on, we've got an input xd. We multiply each of these with a single weight, and then we compute what is called a net input. So I was calling it U, so we can do I equal to 1 to D, Wi xi, or we can express it as W transpose X in vector form. Once we have this net input, what this neuron does is that it applies an activation function on top of it, and then it generates an output that we are going to call Y. So this is the model of the neural network that we discussed. So this is the representation bit of it. If we have a given target for an example, let's say if your target value that you want the neural network to generate for this input X is T, then what we can do is we can have an error function that measures how much of error this neural network generates for a certain value of weights. We can then optimize this error with respect to the weights. And that is how this optimization bit works. Okay, so we've got evaluation and optimization over here. Now what we are going to do is we are going to connect multiple neurons so that the output of one neuron feeds into the next neuron, and we can have multiple neurons in parallel to each other as well. Okay. One important difference in what we are going to discuss now and what we've been discussing earlier is most of our machine learning models were what I called multiple inputs but single output models. So because you had features, a feature vector of which was d-dimensional as input coming into it, and at the same time there was a single output that we called Y. What we are going to do now, or what is possible through these neural networks, is that they can have, these neural network models can have multiple outputs. So they can have multiple inputs, just like you had multiple inputs in, say, a single perceptron or a support vector machine. These can have multiple inputs, but they can also have multiple outputs. And you may want to, let's say you want to predict the age of a person and the gender of the person at the same time, then your X input can be an image, and at the output you want to predict two variables at the same time. So instead of designing two separate models, what you can do is design a single model that allows you to predict both of them at the same time. And you would need a loss function for each of these outputs so that you can measure how much error each variable is producing at the output. So because these neural networks can be multiple input and multiple output, they are going to be a bit more difficult to understand in comparison to these single models. But if you understand this multiple input, single output framework in which you have a single X as input, and then you have an output that you measure to a single variable in loss calculation or in evaluation, all we are going to do is that we'll have a single input, but we'll have multiple outputs, and we'll compare each of those outputs with a target value for that output. So gender would be compared to gender, and age would be compared to age, and so on. And then we'd have a loss function there, and then we're going to optimize all the parameters in this model with respect to the error function. We're going to optimize the error function with respect to the parameters of this model so that we can do optimization. So everything is pretty much the same. It's just that there are going to be multiple inputs and multiple outputs. And within the neural network, or within this model, there are going to be neurons that are going to be connected. So one neuron is connected to every neuron in the next layer, as we're going to call it. And then you're going to have multiple neurons in that layer connected on to the next one. It sounds a bit complicated. Let me show you a figure, and it'll become really easy for you to understand. So this is what is called a multi-layer perceptron. Don't be scared by it. We're just going to break it down into very simple parts, and then hopefully you'll be able to understand. Let's say you've got an input that is d-dimensional. You've got d different features. So each one of those inputs for a given example, or each of those features becomes an input to this model, this whole model. So we can represent it as, if you want to draw a block diagram for it, you have d different inputs for a single example. You have x1 up to x. In this case, we call it xn. So instead of n denoting the number of examples, in this case, it denotes the number of dimensions for a single feature, for a single example. So let's say if you got two-dimensional input, then this n is going to be equal to 2. At the same time, if we have this neural network model that we're calling a multi-layer perceptron, then it has m outputs. Okay, so let's say if you're trying to predict m different values, let's say you're trying to predict 4 different values, then in this case, m is going to be equal to 4. So if you're trying to predict 2 variables, for example, gender of a person and their age, there are only going to be 2 outputs. In our classical machine learning models, like support vector machine, we've seen how these machines can only have a single output. So if you want to reduce this, the complexity of this to gain an understanding, think of that like there's only a single neuron or a single output of this model. So m is equal to 1. And your understanding won't be impacted much by having a larger value of m. Okay. So if you think of this as your input and output now that we're clear about what goes in, an example goes in and predictions come out, right? That's what we want to represent. However, this neural network is composed, of course, of neurons, and these are called, we're going to call these neurons that are at the input, and they represent these features. They aren't exactly neurons, they're just going to be placeholders where we can connect our inputs. So they don't do anything. They just pass on the input for a given feature onto the next neuron. Okay, so this is a single neuron over here that takes in all of the features or input from all of the features, and it's connected to x1, and then it's connected to this x2, xi up to xn. So it's connected to all of the input neurons. So if this neuron over here takes input from takes as input all of the features, and then what it does is that it multiplies each of these inputs with a certain weight value. And we're going to denote those weights as V's instead of W's. I'll explain why, but for now, just understand that we're just going to change the notation a little bit. We're going to call these inputs, these weights, which are multiplied with these inputs as V. So V11 connects over here input X1 to this first neuron. Then we have an input Xi that is connected to this neuron that I'm calling it Z1. The corresponding weight I'm going to call Vi1. So the first subscript indicates what input it is, what feature it is, and then the second one is going to denote what is this connected to. So in this case, it's Vi1, meaning this is the weight for the ith input leading to the first neuron in this layer. Okay, I'll explain the concepts of layers in just a bit in just a moment, but it's important that you understand this notation first. Vn1, of course, is going to be connecting the nth feature, which is going to be given at the input for a given example, to this particular neuron, which is Z1 in this case. So each of these neurons, this neuron over here has n inputs. And if you notice, there is something else going on over here as well. There's an input that is always 1, which gets multiplied by a weight, which is, I'm calling it V01. And if you think about it, this weight over here gets multiplied with this one, this weight over here gets multiplied with this one, and so on. So if you write it in mathematical form, this weight is going to be multiplied with this one. So if you write that as an expression, what we are doing over here is simply we have V11 multiplied by x1, we have V21 multiplied by x2, we have up to so on Vi1 being multiplied with the input xi, and this is again the ith feature, not the ith example. It's really important to understand that. And then we have xn multiplied by this Vn1, and then we have this bit over here. If we write it out, we can write it like V, so instead of having x value, it has just 1. So we are multiplying V01 multiplied by 1. So this becomes the net input. I'm going to call it U1. This becomes the net input for this particular neuron over here. Then what this neuron does is that it applies an activation function on top of this to produce its output, which I'm going to call, so I'm just going to call this net input as Zn1. And then we apply an activation function on top of it, which I'm going to call f, and then this neuron produces an output. If you think about it, this multiplication by 1 is simply adding a bias term, just like we had a bias term in our support vector machines or other linear discriminants that we talked about earlier. So there's nothing too fancy going on over here. This is just a dot product, or we can write it as in the form of a summation that you see over here. We are summing up all the values from I is equal to 0 to n. We have n features, the 0th feature being always 1, indicating the bias. And then we have x, we specify this by saying x0 is always equal to 1. And then we have each weight multiplied by the corresponding input to produce what we call as the total or net input for this particular neuron. The same thing happens for all the other neurons, for a bunch of other neurons over here that I'm saying are in this layer. Okay, so you have this neuron over here, which is connected to all the inputs, but notice it has different weights. So if this neuron is called Zj, let's say j, the value of j is equal to 2, then you can have V01, V10, Vi, so this is going to be, if j is equal to, let's say, 2, then this is going to become V02, V12, Vi2, and Vn2. And then it's going to sum its input, all of these inputs, and apply an activation function on top of that to generate its output. Okay. So if you think of a neural network, what we have done is that we have, instead of using a single neuron, we have used 2 neurons. And you can have p different neurons, each one of them taking all the input features into it, doing the same weight modulation that we discussed for a single neuron, applying an activation function on top of it to generate an output. So at this particular level or layer, we can have as many as p outputs because we have specified that there are p different neurons over here. And then each of these p neurons, there's one important thing. Notice that these p neurons are not interconnected to each other. There are no weights going between these at this level. Okay, so this neuron over here, this one over here, right? So, and similarly, there is no interconnection over here. What happens next is that if we have a single neuron in the output, if we want to produce a single output, so this m is going to be equal to 1, but if we want to produce multiple outputs, this value of m can be larger. Let's assume for the generic case that we have m different outputs that we want for the neural network to generate. And what happens is that we have m different neurons in what is called the output layer. So this is the input layer, remember, and this is the output layer. And because these neurons are now hidden away, they're not visible from the outside and they're not visible from the inside, we're going to call them hidden neurons, okay, or neurons in the hidden layer. So we have got a single hidden layer in this case. We can have multiple ones, but the thing is, the neurons that produce the output are called output neurons. The values or the placeholders, these neurons in the input layer, they just accept the feature values. They don't do any processing on them. They pass these feature values on to the neurons in the hidden layer. And then this is the structure of a multilayer perceptron. Now, if you think about it, let's talk about this neuron over here. I'm just going to use a different color so that we don't mix up different neuron types. So let's say we've got a neuron over here. I'm going to call it Y1. This is going to be the first output. Let's say this is going to be the gender, or it can be the age, whatever. But this is going to be the first output. And this neuron over here is then connected to each neuron in the hidden layer with different weights. And that's why we used V over here to indicate that these are the weights going from the input to the hidden layer. hidden layer neurons, and these W's are going to be the weights leading from these hidden layer neurons to the output layer neurons. So what we have over here is pretty much the same structure repeating itself. We have a neuron that is connected, let's say this neuron 1 is connected to this hidden layer neuron through a weight that we call W11. So when this neuron produces an output, it is transferred onto this neuron over here with through a weight. It is modulated or multiplied with a weight W11. Similarly, this is the weight that connects the jth neuron in the hidden layer to the first neuron in the output layer, and this is the weight over here that connects the pth neuron in the hidden layer to the first neuron in the output layer. And then this neuron pretty much does the same thing as the previous neurons that we talked about. It takes in all of these weights, it takes in all of these inputs, does a sum of products on top of it. Notice there is also a bias term over here that it gets multiplied by this. This one gets multiplied by this bias term over here. And then all of these values are summed up. We can write an expression for that over here. So if you want to write it in an expanded form, then it's going to become, you have W11 connecting the output of this neuron over here to this neuron over here, and that is if we call the output of this particular neuron over here as Z1, then it gets multiplied with W11. Then you have got W21. That's going to be the neuron output of the second neuron of the hidden layer, will be multiplied with this weight W21, and so on. We can have Zj being multiplied by Wj1 up to so on to Zp being multiplied by Wp1. And then we have a bias term that is simply W01, and that's going to be multiplied by 1. So this over here is the bias term. We do a summation over here, and we call that summation y in k, which is the net input of this kth neuron in general. If for this particular neuron that we were talking about, the value of k is equal to 1. And once we have that net input, an activation function is applied on that, just like a regular neuron, and then that produces an output that we are going to call yk. So it sounds really complicated, but it's this repetition of the same thing. A multi-layer perceptron consists of multiple layers of neurons. We've talked about these layers. There's an input layer which accepts these features for a given example. There are hidden layers. There can be more than one, but there are neurons in the hidden layer. The definition of a layer of neurons is that in this particular case, in the case of multi-layer perceptron, each neuron in a layer is going to be connected to every neuron in the previous layer, but not to neurons within its own layer. Okay? And then you have these neurons feeding their output into the next layer, which is, in this particular case, the example that we have is the output layer. That's where we generate the output. So there are layers of units other than the inputs, and the output are called hidden units. So these are called hidden units. There are unidirectional weight connections. So you feed your input from these inputs. They travel through the network onto this first hidden layer of neurons in the forward direction, as we're going to call it. And these neurons then go forward their outputs into the next layer. So these weights are unidirectional. You cannot have these output neurons feeding back to the previous layer for this particular architecture. There are other architectures of neural network where it is possible, but we're not discussing those right now. So these, in a multi-layer perceptron, you have unidirectional weight connections and biases. And what each neuron does is what each neuron does individually as well. It has a bunch of weights associated with that particular neuron, which does a dot product of all the inputs of that neuron. It applies an activation function on top of that, and then it produces an output. You can have different type of activation functions. We've already talked about that. You can have a linear activation function, in which case you have u of x, f of u equal to u. That is, the neuron is going to produce is going to generate its total input as output now. You can also have rectified linear outputs which produce 0 if u is less than 0, and they produce u otherwise. Okay, so this is called a rectified linear unit, and this is called a linear unit or linear activation function. So you can have linear or non-linear activation functions at each neuron. Each neuron within the layer is assumed to have the same activation function, although that is not a strict requirement. So these neural networks, because they have these non-linear activation functions, these are non-linear classifiers. So if you use a linear activation function within each neuron, you'll essentially end up with a linear model, although it may have multiple layers. But if you use different activation functions, non-linear activation functions, then you'll be able to separate non-linearly separable problems as well. Now, if you think about this neural network architecture, there are a lot of different weights over here. I want you to pause the video for a second and calculate how many different weights are there in a multi-layer perceptron if it has n inputs, p neurons in a single hidden layer, and m outputs. Okay, it is going to be a large number. It has a lot of these weights, but if you think about it, changing those weights essentially changes the output of a given neuron. So if you've got an input over here, notice that it gets multiplied by with these weights. Hence, the input into the next neuron is changed if I change this weight. That means by changing this weight, I can control the output of this particular neuron over here. And because the output of this neuron can be changed due to this, then that means this neuron, because it feeds to all of these output layer neurons, their output is going to change as well. Okay, I hope that makes sense. The parameters of this particular machine learning model, which we call multi-layer perceptron, are all of these weights. And by tuning these weights, we can change the output of each of these output layer neurons so that they can match a given target. We're going to talk about evaluation and optimization next, but it's important that you understand all of these representation components. We give a single input. This is where the input is coming in. It gets multiplied with this weights. It produces for each hidden layer neuron a net input, which is acted upon by an activation function to produce an output. That output is then fed over here into this network, into these output neurons, and each of those is multiplied with a corresponding weight to produce a corresponding net input for each of these neurons over here. And then we have an activation function that is applied on top of that to produce the final output of the neuron. So this is the representation of your neural network architecture. If you use nonlinear activation functions, that's a choice that you need to make as a hyperparameter. You can change the behavior of the network. However, in order to produce or tune the network or train the network, we'll be changing the weights. We make certain assumptions here that activation functions should be the same for all of the neurons in the same layer. They don't have to be. This is just a simplifying assumption that we are making right now. Then the input layer just passes the input signal without processing. So it's a linear operation. There is no processing going on within these inputs. Okay, so they're just going to be placeholders. Some people just choose to ignore them or show them in a different way as well. Now, before we move on, if you want to pause the video and think of what are the different types of structural components of this neural network. It's a network because you have an interconnection of different nodes, each of them being a neuron. And what we want is the neuron to produce a certain output. But if you think about it, there are certain components of this. One of the components is it does a dot product. Each neuron does a dot product of its corresponding weights with all of its inputs. Adds a bias term to it. And then the second structural component is going to be the activation function, so that the neuron can generate its output, and that output is connected to all the neurons in the next layer then. Okay, so the activation function is a very important component. It allows you to essentially do nonlinear operations within these networks, within these neurons. If you make them if you keep these activation functions simple, they should be, it would be easier to process. They wouldn't cost too much computation. If you want to make them complex, then that computation is going to be slow. So there's a computational impact or computational time impact of the choice of the activation function. But that's not the whole of the story. Because we produce an output of the neural network, that neural network is controlled by the activation function, right? And once we want to tune the weights of the neural network, essentially we want to take the derivatives of the weights of the output of the neuron, or the error function of the neuron with respect to the weights of the neuron. And in that computation, that we will also be required to take the derivative of the activation functions themselves. So it should be relatively easy to compute the derivatives of those so that we can train in a computationally efficient manner. Okay, so if you want to pause and think about this for a second before we move on, that would be nice. Okay, moving on. So before we actually move to the evaluation part of the structure of multilayer perceptrons, why do we connect neurons? Now I've given you a very low level picture of why we're connecting neurons or how they're connected actually. Now, the real reason we want to connect neurons is that a single neuron is really limited. So it can only make a single cut in the feature space, and that is also going to be linear. When we have multiple neurons, they can produce multiple cuts within the feature space that we are talking about. And then you can have multiple layers of neurons, and each one of those is going to be non-linear. You essentially can approximate very complex functions. As a matter of fact, there is a proof that we haven't talked about that these neural networks with a single hidden layer are able to approximate any function out there in the universe. Okay, so there are universal approximators. So there can be multiple input and multiple output. We've talked about that a bit. And then you have a non-linearity. So if there is a non-linear component in the activation function, you can perform nonlinear classification or work on non-linearly separable data as well. So that's why these neurons are connected. Just to give you some historical perspective, once the first neuron was implemented as a perceptron back in the 1940s and 50s, people started thinking about these multiple neurons, multilayer perceptrons, so that the output of one neuron feeds into the neurons in the next layer, and then those feed into the next layer, and each one of those has an activation function over here. So these neural networks were originally developed, or the ideas for those were originally developed in the 1960s. However, there was a slight problem that we didn't have very efficient computation, and we didn't have algorithms. So there was a computing efficiency part, and then there was an algorithm part that we didn't have sufficient. We didn't have a formula or didn't have an algorithm that would allow us to update these weights in an efficient manner. So these multi-layer perceptrons, or MLPs, and I'm going to call them, these are pretty old, and these have a bunch of other names as well, and it's important to know those as well. If you look at this architecture that we've talked about, not this one, sorry, this one. You can see that this neural network is fully connected. Each neuron at a given layer is connected to all neurons in the next layer. So this is called a fully connected neural network. Although it's important to notice that there are no connections of neurons within the same layer. So it's called a fully connected neural network. And if you think about information flow in these neural networks is in the forward direction. There are no backward flows. So you feed your input features, they go on to the next layer, then they go on to the next layer, and so on. So the direction of flow of information through these neural networks is in this forward direction. So some people also call these multilayer perceptrons as fully connected feed-forward neural networks. Okay, so that's another name for the same thing. Okay, I hope you understand now why we are connecting these neurons. And now we move on to the next bit. Remember, to understand any machine learning model, we talk about representation, evaluation, and optimization. We have talked about representation. How does a neural network take an input and generate its output? What is that structure? We express that structure in the form of different equations, which are shown on your screen. Now, Let's say for a given example, I'm going to indicate example in bold, as a bold, to indicate that it has multiple, it's a vector. And let's say we talk about an example that has, let's say, n different features, and then we talk about the first example being, we can talk about the first example being, sorry, I lost my mouse there. We can talk about this as being x1. So x1 is one example. You can have another example x2 and so on. So these, all of these are vectors of, you can have n different features, each one of them. Let's say for each one of those, you are given a bunch of outputs as target values. Let's say for a given example, let me give you an example data set. So let's say you've got two inputs. So you've got two features. I'm going to call this feature 1 and I'm going to call this feature 2. Let's say you've got a feature 0, 0. The first feature, you've got a single example in which there are two features 0, 0. Then you've got an example 0, 1. Then you've got an example 1, 0. And then you've got an example that is 1, 1. And you can have one output for each example. That is the classical case that we've been talking about. But you can have more than one outputs. So these over here are features, and you can also have outputs or desired outputs or targets, as I'm going to call them. You can have a single output. Let's say if you want to solve the AND problem, then the target output for this one is going to be 0, 0, 0, and 1. So this is the output over here. Let's say if we have such data, and that is how typically we express our data sets in machine learning. We have a bunch of examples. For each example, we have a bunch of features and then a single output. But you can have more than one outputs, because now what you have is a representation that allows you to produce multiple outputs. So let's say you can have an AND output. You can also have an OR output, which is going to be 0, 1, 1, 1. So you can have two outputs. So in this case, if you want to make a neural network for this, you would have two inputs and you would have two outputs. You can have more than two outputs as well. These are going to correspond to the features. This is going to be feature 1, okay, and this is going to correspond to feature 2. And then you can have a number of neurons in the hidden layer. That number is going to be selected as a hyperparameter. So let's say we can have 4 neurons in the hidden layer. And each of these neurons in the hidden layer is connected to each of these inputs. So this happens, okay? And then each of these hidden layer neurons is going to be connected to all the output neurons, okay, as well. So this is the simple structure of your neural network for this case. So in terms of notation, we are going to call the output for a given example. So if this is the first output, I'm going to call it y1 with a 1 in the superscript. And this is going to be y2. We've got two outputs, one corresponding to AND and one corresponding to OR. Okay, and then you can have different examples. Sorry, I should have used it in the subscript. Apologies for that. So this is going to be the first output, and this is going to be the second output for a given example. Okay, so when you feed in an example, let's say you feed in example 0, 0. In this case, it travels through this network, gets multiplied with the weights, is acted upon by activation functions, and then an output is generated for each of these two outputs. And then you have a target value corresponding to each of these outputs. You have a target for AND and you've got a target value for OR for a given example. And then we can compute the difference between the target value and the value your neural network produced at its current value of weights. Let's say if the output for if the kth output, so the first output is yki for the ith example. Let's say I is equal to, we can say this I is equal to 0, then we've got I is equal to 1, I is equal to 2, and I is equal to 3. Let's say we've got 4 examples in total. So we can have the output of each of those examples. The first output gets subtracted from the corresponding target value. Let's say the first output corresponds to this AND. So let's say the output for this neural network is 2 for whatever reasons. then we can have 2 minus 0 because the target is 0. We add that, we square it, and then we do it for the same thing for the other output. Let's say for that, let's say the output is 3, the corresponding target value is 0 again, and we do that. And we do this for all of our examples, so we can sum up the square of all of our errors for all of our outputs for all of our examples. So this is what this sum does. We have a summation over all the outputs, over all the examples that we have in the training data set, and then we can go ahead and compute this sum of squared error loss function. And that is how we can calculate how good or bad are the weights of your neural network. If those weights in the neural network were good, then the output should have matched more closely with the targets that we had in the training data set, and your sum of square errors would have been low. That is not the only loss function that we can use. There are other loss functions, but regardless, the general concept here is we have a way of measuring errors for each of those outputs for a given example. We are going to use this error function or this loss function, and we are going to differentiate this loss function just like any optimization problem. And then we are going to update those weights in the neural network so that those weights force the neural network to produce a corresponding output for a given input so that the output matches the target. There are other loss functions available as well, and that can vary from problem to problem, just like we had discussed earlier. You can have L1 loss, which is simply the sum of absolute values. You can have an L2 loss, which is the sum of squared error loss. You can also have a hinge loss. There's also a squared hinge loss. There's a log loss or cross entropy loss, which is going to be used in multiple classification problems. And there's a Tanimoto loss. There are so many loss functions, we can talk about them all day. But the major point is they simply measure the error between the output and what the neural network is producing. That allows us to then present this learning problem for a given training data set as an optimization problem, and then we can optimize that. Just like we could for our previous networks, even for a single neuron, it's the exact same thing except that we have multiple outputs here. Okay, nothing much. So if you restrict it to m is equal to 1, so if you have a single output, if you have a single output over here, it's pretty much the same thing, right? Except that now we have more weights as well. So we have weights in the hidden layer over here that connect so these neurons are connected to these neurons through these set of weights, and then these neurons are connected to these neurons through these set of weights. So we have more weights as well. So we have more moving parts, and we want to find the optimal values of these weights that result in the lowest error. And that is where optimization happens. However, this problem is more complicated in terms of the optimization landscape. Remember, we talked about the loss function or the loss landscape of support vector machines and other linear discriminants, and we said that those are convex because the resulting optimization problem is convex. Now, the optimization problem in this case is simply minimize the error, which is the sum of squared errors, let's say. So you have got this error function over here. I'm just going to copy it over. So it's going to be yki minus tki squared summed over k and over I. Okay. But if you notice, this output is generated by the output layer neurons, and there we can control this output by changing the weights of these or changing these weights, right? At the same time, so we are optimizing it with respect to all the weights W, but we are also optimizing it with respect to all the weights in the previous layer. So this is the optimization problem for a given neural network. But if you think about it, this output is depending upon the activation function, which is nonlinear, and it may not be convex. And that can lead to very complex optimization, and your convergence is no longer guaranteed because you don't have a convex optimization problem. So that leads to a non-convex optimization problem, which are really difficult to optimize using gradient descent. So when we talked about linear discriminants with gradient descents, I told you that because the representation is linear and every linear function is convex, and the error function is, the loss function is also convex, therefore your whole optimization problem becomes convex, and convex functions have a single global optima, and then that means that you can solve for that optimization problem using gradient descent. In the case of these multilayer perceptrons, because your activation functions are nonlinear and your loss can also be non-convex, so that leads to a difficult to solve optimization problem. So here, if you start a neural network if you start your optimization process for a certain set of weights, you may converge after the gradient descent to a different point. If you start somewhere else, you may converge to a different local minima. So the convergence is not guaranteed. So solving the optimization problem for neural networks is more difficult than it was for simple linear discriminants. That is why you really need to understand all the moving parts so that you can understand what to do when optimization fails for a neural network. And believe me, it will fail when you're training your neural networks. Okay, so the basic process is simple, conceptually at least. You compute the gradients of this error function. Okay, so this is your error function. You compute its gradients. I'm just going to call this error function E. So you compute its gradients with respect to the weights W, and you compute its gradients with respect to the weights V, and then you apply gradient descent. This is simply an equation of the gradient descent. You optimize it with respect to each weight. You have a current value of the weight. You compute your loss value at that particular value of weight. You take a step in the negative direction by a step size alpha, and this is your gradient descent update. And you keep on doing that until you find your optimal values of weights. And this is how you optimize a neural network or a multilayer neural network. So we have talked about, in this part of the lecture, we've talked about how you can train a neural network, how you can represent a neural network, a multilayer perceptron. It's pretty simple. You have input features coming in into the input neurons, which pass their outputs, which pass these features as is into neurons in the hidden layer, and each of those neurons is connected to all the features in the input. Then what happens is you compute your net input, you apply an activation function, produce an output, which is fed to all neurons in the next layer, which each of those neurons also sums up all of these inputs by multiplying them with corresponding weights, computes a net input, applies an activation function, and then generates an output. So that was the representation bit. We expressed it mathematically. We then talked about a loss function or different losses, how you can measure error for a given neural network. And then we talked about optimization. All we need to do is to change these weight values using some algorithm so that our neural network is then tuned to produce a certain output. Okay. So next we are going to do a simple visual analysis of how you can train a neural network using this playground in TensorFlow. What I would like you to do is to think about the role of our hyperparameter choices. How many hidden layers do we have? How does that impact the number of weights? What if we have more neurons in the hidden layer? How do we select that? Those are all the sorts of problems that we'll be talking about when developing these practical multilayer perceptrons. Okay, thank you.